World War II is often described through battles, leaders, and borders.
But behind every advance and retreat stood a second conflict, a struggle to detect, calculate, manufacture, heal, transport, and destroy more effectively than the opponent. That struggle produced machines that would shape the modern world. It also produced suffering on an industrial scale. This is not a story about one nation possessing genius while another did not. Scientists, engineers, factory workers, soldiers, prisoners, and civilians across many countries contributed to wartime technology. Some ideas were developed independently in more than one place. Others crossed borders before the war, were captured, copied, or improved afterward.
And many famous wartime inventions were not invented between 1939 and 1945 at all. They were older concepts transformed by emergency funding, mass production, and brutal operational experience. So what counts as an invention?
A laboratory prototype is not the same as a reliable field system.
A brilliant machine is not useful if it cannot be maintained, supplied, or produced in numbers.
The war rewarded complete systems, a sensor connected to a communications network, a vehicle supported by fuel and spare parts, a medicine manufactured in millions of doses, an aircraft matched with trained crews, airfields, and doctrine. This documentary examines those systems without asking which flag deserves the most credit.
The evidence shows something more complicated. Germany fielded operational ballistic missiles and jet fighters, but struggled to translate them into strategic victory. Britain built an integrated air defense network around radar. The United States turned research into extraordinary industrial scale.
The Soviet Union combined design choices with mass production suited to an immense land war. Japan developed advanced naval weapons and aircraft, yet faced severe material and industrial constraints. Every belligerent made innovations. Every belligerent also made costly mistakes. Technology did not make the war clean. It extended vision, speed, range, and destructive power. It saved lives in hospitals and took them in cities. To understand what was truly invented, we have to examine not only the machines, but how they were used, who built them, and who paid the price.
Chapter 2. Radar, Seeing Beyond Sight. Radar did not begin with the Second World War.
The scientific basis went back to 19th century work on electromagnetic waves, and several countries investigated radio detection before 1939. What the war accelerated was the transformation of scattered experiments into dependable networks. Britain's chain home system is a clear example.
Tall transmitting towers along the coast sent radio pulses outward.
When those pulses reflected from aircraft, receiving stations could estimate range and direction.
Chain home was not a magic screen that identified every aircraft perfectly. It was relatively crude, vulnerable to errors, and dependent on skilled operators. Its decisive value came from integration.
Reports flowed to filter rooms, command centers, and fighter stations. The system helped commanders place limited aircraft where they were needed instead of maintaining wasteful patrols everywhere. Germany also developed and deployed effective radar sets, including Freya for early warning and Würzburg for more precise tracking. The United States, Soviet Union, Japan, Italy, and other states pursued their own systems with different priorities and levels of success. Radar became an international technological contest in which the hardware, operating frequencies, operator training, and command structure all mattered. One of the war's most important electronic devices was the cavity magnetron, developed into a practical high-power form by John Randall and Harry Boot in Britain in 1940. It generated short-wavelength microwave energy with enough power for compact, precise radar. Shared with the United States through the TIZARD mission, it became central to an enormous research and production program.
Microwave radar could fit aboard aircraft and ships and could resolve smaller targets than many earlier systems. Airborne interception radar helped night fighters locate bombers in darkness. Maritime radar helped aircraft find submarines and ships across open water. Ground mapping radar offered navigators an electronic image of coastlines and cities, though never with the certainty of modern digital maps. Radar-directed anti-aircraft guns improved defensive fire. By 1945, radar had become a family of technologies rather than a single invention. Its limitations were equally important. Sea clutter, weather, terrain, electrical failure, and deliberate interference could conceal or confuse a target. Operators interpreted ambiguous signals under pressure. Friendly aircraft could be misidentified. A sensor did not remove uncertainty, it changed the kind of uncertainty commanders faced. The enduring invention was therefore not merely an antenna or transmitter. It was networked awareness, machines gathering information, people interpreting it, and commands moving quickly enough to influence an event. Modern air traffic control, weather observation, navigation, and remote sensing inherited much from that wartime acceleration. Chapter 3. Sonar and the Underwater War. Beneath the Atlantic, radio waves were of little use. Water absorbs them rapidly, so the struggle against submarines depended on sound. Active sonar, known in British service as ASTIC, sent a sound pulse through the water and listened for an echo. Passive hydrophones listened for machinery, propellers, and other noises without transmitting. Again, the basic concept predated the war. Underwater detection had developed after the Titanic disaster and during the First World War. By 1939, several navies possessed working systems. Yet early sonar had serious limits. It usually searched a narrow area, performance changed with water temperature and layers, and contact could be lost when an escort ship passed directly over a submarine to drop depth charges. Wartime innovation attacked the whole problem. Escort ships received improved sonar. Aircraft used radar to find surfaced submarines, especially at night. High-frequency direction finding, often called HFDUF, located brief radio transmissions from U-boats. Intelligence from decrypted messages informed convoy routing. Searchlights, depth charges, ahead-throwing weapons, patrol aircraft, escort carriers, and trained analysis teams became pieces of a connected anti-submarine system. The submarine war produced countermeasures and countermeasures. German submarines adopted radar warning receivers, acoustic torpedoes, snorkels, and new tactics. Allied forces jammed or deceived some systems and improved their own sensors. No single device won the Battle of the Atlantic. The balance changed when detection, intelligence, escort numbers, air coverage, weapons, shipbuilding, and merchant convoy discipline worked together. This distinction matters because technological history often gives the machine all the credit. Sonar could indicate an echo, but crews had to classify it. A whale, wreck, temperature layer, or friendly ship could create confusion. Aircraft could force a submarine underwater, but endurance and weather controlled how long they could search. An escort carrier expanded air cover, but it demanded ships, pilots, maintenance, and fuel. The same acoustic principles later expanded into oceanography, fisheries, underwater mapping, and navigation. But their wartime development came from a campaign in which merchant sailors died in vast numbers and submarine crews faced exceptionally high mortality. The technical record cannot be separated from that human cost. Chapter 4. The Invisible Electronic Battle. Once armies depended on radio and radar, the electromagnetic spectrum became a battlefield. Signals could be intercepted, located, jammed, imitated, or used to deliver false information. Electronic warfare was not spectacular to watch, but it could decide whether bombers found a target or defenders found the bombers.
One of the simplest countermeasures was chaff. British forces called it window. Aircraft released bundles of thin metallic strips cut to reflect radar energy. The sky filled with false echoes, making it difficult for operators to distinguish formations from clouds of foil. Germany had investigated a similar idea called Doppel but initially hesitated to use it, fearing retaliation in kind.
Britain first used window operationally during the bombing of Hamburg in 1943. Chaff did not make aircraft invisible.
Radar frequencies changed, operators learned new interpretation methods, and defenders combined visual reports, sound, and multiple sensors. But it demonstrated a lasting principle: a cheap countermeasure can temporarily reduce the value of an expensive detection system. Jamming transmitters broadcast noise or deceptive signals. Navigation beams were bent, masked, or copied. Radio operators monitored the spectrum for patterns. This contest required physicists and mathematicians, but it also required technicians who could repair equipment in cold aircraft, crowded ships, and mobile trucks. The proximity fuse represented a different electronic achievement. Traditional anti-aircraft shells were set to explode at a predicted time or upon impact. A proximity fuse contained a miniature radio transmitter and receiver. When the reflected signal changed as the shell approached a target, the fuse detonated nearby. Engineers had to make vacuum tubes and components small enough to fit inside a projectile and rugged enough to survive the violent acceleration of being fired from a gun. The United States and Britain carried out much of the development, drawing on research teams, industry, and large-scale testing. Proximity fuses increased the effectiveness of anti-aircraft fire and were later used against ground targets. Their use was initially restricted in some theaters because leaders feared an unexploded shell might reveal the technology. Electronic warfare exposes another problem with the word invention. Chaff was conceptually simple. The proximity fuse was technically intricate. Both changed combat because they were delivered at the right scale and connected to tactics. Complexity alone did not determine importance. After the war, electronic countermeasures, radar warning, and precision fusing became permanent parts of military systems. Civil aviation and spaceflight benefited from miniaturized electronics and improved reliability. Yet the same techniques also made later weapons more effective. Progress had no single moral direction, its meaning depended on its application. Chapter 5. Computers, ciphers, and calculation. The Second World War did not create computation from nothing. Mechanical calculators, punched card machines, analog computers, and theoretical work on algorithms already existed. The war created urgent problems that demanded more speed: artillery tables, cryptanalysis, aerodynamics, logistics, and atomic research. At Bletchley Park, British codebreakers attacked encrypted German communications. The story included Polish mathematicians who had reconstructed the Enigma machine before the war and shared their work with Britain and France in 1939. British-designed bombs then helped search possible Enigma settings. Human organization remained central. Intercepted messages had to be collected, indexed, compared, and interpreted. Colossus was developed for a different cipher system, the Lorenz teleprinter traffic used by German High Command. Engineer Tommy Flowers designed an electronic machine using large numbers of vacuum tubes. It read paper tape at high speed and tested logical patterns that helped analysts identify cipher settings. Colossus was programmable in a limited sense, but it was not a general-purpose stored program computer. Its secrecy after the war complicated later accounts of computing history. In the United States, the Army funded ENIAC to accelerate ballistic calculations. John Mauchly and J. Press per Eckert led its design at the University of Pennsylvania. Women mathematicians had previously calculated firing tables by hand and with desk machines.
6 women became ENIAC's first programmers, translating procedures into cables, switches, and function tables.
ENIAC was completed too late for its original wartime purpose, but the project and the knowledge surrounding it influenced post-war computer development. Germany used sophisticated analog guidance and calculation systems, while Japan and the Soviet Union also used mechanical and electromechanical methods. Across all sides, most wartime calculation was still performed by people, often women whose labor was described by the same word, computers. Code breaking did not mean that every encrypted message was read. Systems varied, keys changed, operators made mistakes, and intelligence agencies had to protect the secret by avoiding responses that revealed too much. Intelligence was combined with reconnaissance, captured documents, prisoner interrogation, and traffic analysis. A decrypted message could be misunderstood or arrive too late. Wartime computing introduced a new relationship between people and electronic machines. Machines could test patterns faster than human teams, but humans framed the problem, prepared the data, built the circuits, and judged the result. The lasting revolution was not that machines replaced thought. It was that certain forms of reasoning could be translated into repeatable electronic operations at unprecedented speed. Chapter 6. Jet propulsion. The jet engine is another invention with multiple origins. British engineer Frank Whittle patented a turbojet concept in 1930. German engineer Hans von Ohain developed a different design later in the decade. In 1939, the experimental Heinkel He-178 became the first aircraft to fly using turbojet power. Britain flew the Gloster E.28/39 in 1941. The war pushed both countries from experiment toward combat aircraft. A turbojet compresses incoming air, mixes it with fuel, burns the mixture, and uses the expanding gas to drive a turbine and produce thrust. The concept was elegant, the materials problem was severe. Turbine blades operated at extreme temperature and rotational speed. Engines required alloys, precise manufacturing, reliable fuel systems, and maintenance knowledge that barely existed. Germany's Messerschmitt Me-262 became the first operational jet fighter. It was significantly faster than contemporary piston-engine fighters, but its engines had short service lives and demanded scarce materials and careful handling. Fuel shortages, training losses, bombing, production disruption, and Allied air superiority restricted its effect. A persistent myth claims that a single order to use it as a bomber alone delayed the aircraft and changed the war. The evidence shows a more complicated reality in which engine development and industrial conditions were fundamental limits. Britain's Gloster Meteor also entered service during the war. It initially defended against V-1 flying bombs and later operated over Europe. It did not meet the Me-262 in combat. Both aircraft demonstrated that jet propulsion was practical, but neither transformed the war's final outcome. Other countries pursued related research. Italy flew the Caproni Campini in .1, which used a motor jet arrangement rather than a true gas turbine. The United States developed jets with British technical assistance. Japan built experimental aircraft influenced by German information but worked under deteriorating industrial conditions. Jet history illustrates why firsts can mislead. The first patent, first running engine, first flight, first operational squadron, and first effective mass-produced design can belong to different people and countries. The wartime breakthrough was collective and uneven. It combined theory, metallurgy, machining, aerodynamics, fuel, and flight testing. After 1945, captured documents, engineers, and aircraft accelerated programs in the victorious powers. Commercial aviation eventually connected continents at jet speed. Military jets became faster and more capable, but also more expensive and destructive. The passenger aircraft and the jet bomber emerged from the same engineering foundation.
Chapter 7. Rockets and Guided Weapons.
Rockets were ancient, and modern liquid-fueled experimentation existed before the war. Robert Goddard in the United States, Hermann Oberth in Germany, Konstantin Tsiolkovsky in Russia, and many others contributed to the pre-war foundation.
During the conflict, rockets developed in several directions. The Soviet Katyusha launcher fired salvos of unguided rockets from trucks. It was less accurate than conventional artillery but could deliver intense fire quickly and relocate before counterfire. German Nebelwerfer systems and Allied rocket artillery followed related principles. Aircraft carried rockets against ground and naval targets. Landing craft fired massed barrages before amphibious assaults. Germany's V-2 was the first long-range guided ballistic missile used in war. Designed by a team associated with Werner von Braun and developed at Piedmont, it rose beyond the atmosphere on a ballistic path and descended at supersonic speed. No defense could intercept it with the technology of the time. Its gyroscopes, guidance, pumps, and liquid-fueled engine represented a remarkable technical achievement. But describing the V-2 only as a path to space erases the conditions of its production. After bombing damaged Piedmont, assembly moved underground to the Mittelwerk. Prisoners from the Mittelbau-Dora concentration camp worked in lethal conditions. More people died in production than were killed by the weapons attacks. The missile consumed large resources while delivering a relatively small explosive payload with poor accuracy. It created terror, but did not offer Germany a rational route to strategic victory. Guided weapons also appeared in the air and at sea. Germany used the Fritz X radio-guided glide bomb and the HS-293 against ships. Operators steered them visually after release, which exposed the link to jamming and required favorable conditions. The United States developed radar-guided and television-assisted weapons, with mixed wartime results. Japan deployed guided weapons including the human-piloted Oka, fusing technology with a doctrine of deliberate sacrifice. The V-1 flying bomb used a pulsejet and mechanical guidance to strike a preset area. It was cheaper than the V-2 and could be intercepted by fighters, anti-aircraft guns, and balloons. Both V-weapons targeted population centers and demonstrated how guidance could extend bombardment without placing a crew over the target. After the war, the United States and Soviet Union competed for German specialists and hardware. Their rocket programs led to ballistic missiles and space launch vehicles. Space exploration, weather satellites, and global communications emerged from this legacy, as did weapons capable of crossing continents with nuclear warheads. The same trajectory points upward towards scientific discovery and outward toward mass destruction. Chapter 8. Armored Warfare and Mechanical Design. The tank was a First World War invention. What changed after 1939 was the combination of armor, firepower, mobility, radios, optics, recovery vehicles, and industrial production. Popular comparisons often reduce tanks to armor thickness and gun size. Armies experienced them as systems. The Soviet T-34 combined sloped armor, wide tracks, a diesel engine, and a design that could be produced in very large numbers. Its early versions had weaknesses in visibility, crew arrangement, transmissions, and command communication. Later improvements addressed some problems while preserving production. The T-34's significance lay not in perfection but in a powerful balance of characteristics suited to Soviet operational needs and industrial evacuation. Germany's Panther and Tiger mounted formidable guns and protection. The Panther introduced sloped armor and strong long-range firepower but suffered early mechanical problems and required substantial maintenance. The Tiger was tactically dangerous yet heavy, complex, and expensive. German armored units also depended on less celebrated vehicles, captured equipment, horse-drawn transport, and repair organizations.
The American M4 Sherman was not invulnerable and was outgunned by some later German tanks in direct engagements. Its advantages included mechanical reliability, standardized production, a powered turret, radios, and the ability to be shipped, maintained, and recovered across distant theaters. British forces adapted the Sherman Firefly to carry a powerful 17-pounder gun. Specialized armored vehicles cleared mines, laid bridges, threw flames, or carried engineering equipment. Japan designed tanks for its own operational assumptions and industrial conditions, often prioritizing mobility and support for infantry. Their lighter armor became a severe disadvantage against later Allied weapons. Italy produced a range of armored vehicles but faced limitations in engines, armor, and manufacturing. No design existed outside its economy and doctrine.
Small inventions affected crews as much as dramatic ones. Better periscopes improved awareness. Radios allowed coordination. Stabilizers offered limited firing capability on the move. Diesel and gasoline engines created different trade-offs. Tracks, filters, lubricants, and cooling systems determined whether a vehicle survived mud, dust, snow, and distance. Anti-tank weapons evolved alongside armor, shape-charge warheads, recoilless systems, improved mines, high-velocity guns, and infantry weapons such as the Panzerfaust and bazooka. Each solution encouraged another layer of protection or a new tactic. The central lesson was logistical. A tank without fuel was a bunker. A tank without spare parts became scrap. A technically superior vehicle could be less useful than a reliable vehicle available in larger numbers with trained crews and repair support. Wartime armored innovation therefore belonged as much to factories, railways, depots, and workshops as to designers. Chapter 9. Amphibious Engineering and Logistics.
Some of the war's most consequential inventions were built to move supplies rather than fire weapons. Amphibious operations required armies to cross water, land on defended shores, unload vehicles, clear obstacles, build roads, and sustain millions of people without an intact port. Specialized landing craft existed before the war, but they were developed and produced on an unprecedented scale.
Flat-bottomed craft carried infantry onto beaches.
Larger vessels delivered tanks and trucks.
Landing ships could cross oceans and open bow doors near shore.
These designs were compromises: seaworthiness, shallow draft, cargo capacity, and ease of mass production pulled in different directions. The DUKW combined a truck with a watertight hull, propeller, bilge pumps, and a system that allowed tire pressure to be adjusted for different surfaces. It could carry cargo from ship to shore and continue inland without transferring the load. The vehicle was not glamorous, but it reduced one of logistics' most persistent problems: handling cargo at each boundary between sea and land. The Bailey Bridge used prefabricated steel panels that could be transported by truck and assembled by soldiers without heavy construction equipment.
Different configurations carried different loads and spans. It allowed engineers to replace destroyed bridges quickly, keeping fuel, ammunition, food, ambulances, and reinforcements moving.
The Mulberry artificial harbors were designed for the Normandy invasion. Concrete caissons, sunken blockships, floating pier heads, and flexible roadways created protected unloading areas off open beaches. A severe storm destroyed the American Mulberry and damaged the British one, but the surviving harbor supported the buildup while captured ports were restored. The invention was not a single object, it was a temporary port assembled across the English Channel. Pluto, the pipeline under the ocean, aimed to move fuel from Britain to forces in Europe. Its early contribution after D-Day was more limited than later legend sometimes suggests, because ports, tankers, and other methods carried much of the initial fuel. As the pipeline network expanded, it became more useful. This is another reminder to separate engineering achievement from exaggerated claims. Japanese forces pioneered and refined difficult amphibious operations early in the war, using coordinated landings across the Pacific and Southeast Asia. Later, constrained shipping and Allied submarine attacks devastated Japanese logistics. In the Pacific, American naval construction battalions created airfields and bases across islands, while specialized amphibious vehicles crossed reefs and beaches. Logistics rarely receives the attention given to weapons, yet the war was won and lost through movement. Standardized containers did not yet dominate global trade, but pallets, drums, jerrycans, forklifts, portable cranes, and disciplined documentation increased flow. The true invention was a chain in which each link was designed to connect with the next.
Chapter 10. Medicine under extreme pressure.
Wartime medicine saved lives, but it did so inside a catastrophe that medicine could not redeem. The conflict created millions of wounds, burns, infections, disabilities, and psychological injuries. Advances emerged because the need was overwhelming and governments supplied resources on a scale rarely available in peace.
Alexander Fleming observed penicillin's antibacterial effect in 1928.
It was not a wartime discovery. The essential wartime change came from the Oxford team led by Howard Florey and Ernst Chain, which demonstrated therapeutic potential, and from British and American cooperation that solved problems of cultivation, extraction, and mass production. Deep tank fermentation and improved strains helped turn a scarce laboratory substance into a medicine available for the Normandy campaign.
Penicillin did not cure every infection, and resistance was recognized early. Sulfa drugs remained important.
Surgical cleaning, vaccination, sanitation, and evacuation often mattered as much as any single medicine. Yet antibiotics sharply improved the treatment of many bacterial infections that had killed wounded people in earlier wars.
Blood medicine also advanced.
Plasma could be stored and transported more easily than whole blood, although it could not replace red cells in every situation.
Blood banks, typing procedures, donor programs, refrigerated transport, and standardized equipment created a supply system.
Charles Drew's work on blood storage and large-scale plasma programs was influential, even as racial segregation shaped American donation policies and exposed the contradiction between scientific practice and social prejudice. Mobile surgical units moved specialized care closer to the front.
Triage sorted patients by urgency and likelihood of benefit.
Air evacuation shortened transport time in some theaters. Improved splints, anesthesia, burn treatment, vascular techniques, and rehabilitation increased survival. Nurses, medics, stretcher bearers, drivers, laboratory staff, and sanitation teams were essential parts of the system.
Not all medical activity was ethical.
Nazi physicians conducted murderous experiments on prisoners.
Japan's Unit 731 carried out biological warfare research and lethal human experimentation.
Some Allied research also crossed ethical boundaries, including experiments conducted without standards of informed consent that would be expected today.
The post-war Nuremberg Code emerged partly from confronting medical crimes, though ethical reform remained incomplete. Psychiatric casualties challenged armies that still used stigmatizing terms and uneven treatments.
Military medicine increasingly recognized that prolonged combat could disable people without a visible wound. Approaches varied, and many veterans received inadequate support after returning home. The medical legacy was therefore both technical and institutional. Antibiotics, transfusion systems, trauma surgery, rehabilitation, and organized clinical research expanded after the war. But the record also demonstrated why medical progress requires consent, accountability, and respect for human beings. Skill without ethics can become another instrument of violence. Chapter 11. Materials, Fuel, and Mass Production. Every advanced weapon depended on ordinary materials. Rubber sealed engines and made tires. Aluminum formed aircraft.
Copper carried electrical current. High-octane fuel increased engine performance.
Shortages redirected research as powerfully as any military requirement. When Japanese expansion cut the United States and its allies off from much of Southeast Asia's natural rubber, the United States launched a vast synthetic rubber program. The chemistry was not new. Germany already had major experience producing Buna synthetic rubber because of its own resource strategy. The American achievement was rapid scale. Government-financed plants, company-shared processes, and production expanded from a limited pre-war base to an industry capable of supplying vehicles and aircraft. Germany produced synthetic fuel from coal, reducing dependence on imported petroleum but at high financial and energy cost. Allied bombing of fuel plants and transportation networks severely constrained German operations late in the war. Japan faced an even harsher oil crisis. Its decision for war was tied partly to access to resources, but conquest could not protect the long maritime supply lines needed to bring those resources home. Metallurgy shaped every aircraft engine and gun barrel. Nickel, chromium, molybdenum, and other alloying elements were scarce. Engineers substituted materials, redesigned parts, and accepted shorter service lives. Germany's late-war jet engines illustrate the trade-off. Limited access to heat-resistant metals forced designs that could perform impressively but wore out quickly. Mass production was itself a field of innovation. The American Liberty Ship program used standardized designs, prefabricated sections, and welding to build cargo ships rapidly. Welding brought advantages in new failure modes, including brittle fractures that required investigation. Aircraft factories broke complex machines into repeatable operations performed by a greatly expanded workforce. The Soviet Union relocated enormous industrial capacity eastward after the German invasion. Factories operated under brutal conditions while designs were simplified for output and repair. Germany increased armament production even under bombing, but dispersed factories, shifting priorities, labor shortages, and transportation collapse imposed growing costs. Japan's industrial system could not match the material volume of the United States and suffered from blockade and bombing. Millions of women entered or moved within industrial workforces, but the image of wartime liberation is incomplete. They often received lower pay, faced discrimination, and were encouraged or forced out of jobs after the war. Colonial subjects and segregated workers contributed labor and resources while denied equal rights. Forced labor was central to the Axis war economy, especially as manpower shortages deepened. Prisoners of war, concentration camp prisoners, deported civilians, and occupied populations worked under coercion, starvation, and deadly conditions. Some celebrated weapons cannot be separated from this exploitation. Mass production magnified design choices. A small saving in material multiplied across 1 million parts. A maintenance problem multiplied across thousands of vehicles. The war accelerated statistical quality control, interchangeable components, production engineering, and operations research. These methods later reduced the price of civilian goods. They also revealed how completely modern violence depended on administration and industry. Chapter 12. Atomic Energy. No invention better represents the war's combination of science, organization, secrecy, and moral consequence than the atomic bomb. Nuclear physics had developed internationally during the 1930s. Scientists in Germany discovered nuclear fission in 1938. And Lise Meitner and Otto Frisch correctly interpreted the process. Refugee scientists warned that Nazi Germany might pursue a weapon. The United States created the Manhattan Project with British and Canadian cooperation. It linked universities, military administration, private companies, and vast secret industrial sites. Oak Ridge separated uranium isotopes. Hanford produced plutonium. Los Alamos designed weapons.
On December 2, 1942, the Chicago Pile 1 team led by Enrico Fermi achieved the first controlled, self-sustaining nuclear chain reaction. The project required theories at the frontier of physics, but it also required mining, chemistry, construction, electrical power, precision machining, and tens of thousands of workers. Many workers did not know the purpose of their tasks. Communities were displaced to build facilities. Uranium came through global supply networks. The project cost billions of wartime dollars. Germany maintained a nuclear research program but did not come close to producing an atomic bomb. Historians debate the intentions and choices of individual scientists, but the material record shows a program fragmented by priorities, resources, and incorrect or incomplete assessments. Japan also conducted limited nuclear research without the industrial foundation for a weapon. The first nuclear explosion, the Trinity test, took place in New Mexico on July 16, 1945. The fallout affected nearby communities, whose exposure was not properly acknowledged for decades. On August 6, the United States dropped a uranium bomb on Hiroshima. On August 9, it dropped a plutonium bomb on Nagasaki. Japan announced surrender days later. The bombings killed tens of thousands immediately and many more from burns, injuries, and radiation. Most victims were civilians. Historians continue to debate the role of the bombs, Soviet entry into the war against Japan, blockade, internal Japanese politics, and alternatives to invasion. A neutral account does not pretend that this debate is settled by a slogan. It distinguishes evidence from counterfactual claims and recognizes the human beings beneath strategic calculations. Atomic weapons did not simply end one war. They began a nuclear age. The Soviet Union tested a bomb in 1949, and an arms race followed. Nuclear reactors later produced electricity and research isotopes. Nuclear medicine saved lives. But civilian and military uses remained linked through expertise, materials, and political institutions. The atomic project changed the relationship between science and the state. Governments learned that concentrated money, secrecy, and large laboratories could push fundamental research toward a specific goal. This model shaped the Cold War, space exploration, and modern research. It also placed scientists inside decisions capable of destroying cities. Chapter 13. The Human System Behind the Machines. Inventors rarely worked alone. Wartime photographs often show a famous engineer beside a machine, but outside the frame stood draftspersons, machinists, secretaries, test pilots, mathematicians, inspectors, radio operators, mechanics, and laborers. Their accumulated decisions turned concepts into working systems. Women performed vital technical work in every major combatant society. They programmed early computers, assembled aircraft, calculated trajectories, operated radar, drove vehicles, treated wounds, and served in uniform. In the Soviet Union, women also flew combat aircraft and served as snipers and medical personnel near the front. Their opportunities varied widely, and recognition often arrived late. The war mobilized colonial empires. Soldiers and workers from India, Africa, the Caribbean, Southeast Asia, and the Pacific supported campaigns and supply networks. Raw materials came from territories whose populations had little control over imperial policy. Technological histories that count patents but ignore extraction present an incomplete picture. Scientists displaced by persecution made major contributions to Allied programs. Nazi racial policy expelled or murdered talent that Germany might otherwise have used. At the same time, the Allies maintained their own discrimination. Black Americans served in segregated units and faced barriers in factories and laboratories. Japanese Americans were incarcerated by the United States even while some family members served in its armed forces. After the war, both the United States and Soviet Union recruited German specialists. American Operation Paperclip brought engineers and scientists to work on military and space programs, sometimes minimizing or concealing their connections to the Nazi system. Soviet authorities transferred specialists and equipment east. Technical value often competed with accountability. Failure also drove innovation. Aircraft crashed in tests. Torpedoes ran too deep or failed to explode. Tanks broke down. Radar screens produced false returns. Medicines caused reactions. Bridges collapsed. Organizations that identified errors and corrected them usually improved faster than organizations that had failure to satisfy political expectations. This is one of the war's most transferable lessons. Innovation depends on information moving upward as well as orders moving downward. A brilliant central plan can be defeated by suppressed evidence. A modest design can become effective when users report problems, factories respond, and training evolves. The machines mattered. But the quality of institutions decided whether machines became reliable capability. People created the data, judged the trade-offs, and absorbed the consequences. Any honest history of invention must restore them to the frame. Chapter 14. What the war actually changed. By 1945, the world possessed operational radar networks, electronic computers, jet aircraft, ballistic missiles, mass-produced antibiotics, synthetic materials, advanced amphibious systems, and nuclear weapons. The list can sound like a sudden leap into modernity. The real change was less tidy and more profound. First, the war compressed time. Ideas that might have developed over decades received enormous budgets and immediate testing. A prototype could move from a laboratory to mass production with risks that peacetime institutions would not accept. Second, the war joined disciplines. Physicists worked with engineers, military staffs, factories, and operators. Medicine became a supply chain problem as well as a clinical one. Radar became valuable through communications and command. Innovation moved from isolated objects toward integrated systems. Third, production became part of design. A weapon that existed only in small numbers could be tactically impressive but strategically marginal. Reliability, repair, training, fuel, and standardization often mattered more than maximum performance. Fourth, information became a weapon. Detection, code breaking, operations research, weather forecasting, and computation helped commanders allocate resources. The modern world of sensors and data owes much to these systems, but more information did not eliminate human judgment or moral responsibility. Fifth, the war proved that beneficial and destructive technologies could share the same foundation. Rocket engines launched weapons in spacecraft. Nuclear physics produced bombs and medical isotopes. Computers calculated artillery tables and later supported science, business, and communication. Antibiotics saved soldiers and civilians while their overuse encouraged resistance. No belligerent nation had a monopoly on intelligence, courage, cruelty, or error. Political systems shaped what could be researched, who could participate, how truth traveled, and whose lives were treated as expendable. Those differences matter. Neutrality does not mean erasing responsibility for aggression, occupation, genocide, forced labor, strategic bombing, or attacks on civilians. It means applying evidence consistently and refusing to turn technical history into admiration without context. The Second World War did not invent the modern world by itself. It accelerated older currents and redirected them through 6 years of global violence. Its laboratories and factories created tools that still surround us. Its ruins warn what those tools can do when capacity outruns restraint. The most important question is not which side invented the most.
It is what societies choose to build, what evidence they accept, whose labor they recognize, and what limits they place on power.
Machines extend human intention. They do not absolve it.
That is the documented record: innovation under pressure, achievement inseparable from consequence, and a technological legacy that remains both useful and dangerous.